Hi there, I am Ümit Alkuş. In this video, we will solve one problem in chapter 24. A metallical spherical shell of radius r equal to 3.2 centimeters has a total charge of Q, which is 4.6 microcoulombs. Relative to infinity, find the electric potential at radial distance r equal to 4.2 centimeters, 3.2 centimeters, and 2.2 centimeters. In order to solve the problem, if we use the formula for the potential difference, V final minus V initial, we have negative line integral from initial to final, the electric field E dot, the infinitesimal path vector dr at position r. If we choose the final point as the infinity, potential at infinity becomes 0. Therefore, we have V initial equals the line integral E dot dr from initial to final, where final is infinity. According to our problem, we can write potential at r Vr equals the line integral E dot dr from r to infinity. In A, r is 4.2 centimeters, which is greater than the radius of the shell, 3.2 centimeters. Therefore, this point is outside the sphere. According to the shell theorem, the charge on the sphere can be considered as if it were concentrated at the center. Therefore, the electric field of this point charge at position r is calculated by the formula K times Q over r squared r hat, where r hat is the radially outward direction. Also, according to this problem, the infinitesimal vector dr is expressed as dr times r hat. If we put these expressions into the formula for Vr, we obtain Vr equals the integral from r to infinity K times Q over r squared r hat dot dr times r hat. R hat dot r hat gives 1, since r hat is the unit vector and r hat is parallel to r hat. So we obtain kq times the integral from r to infinity dr over r squared, since k and q are constants. We know that the integral of dr over r squared is negative 1 over r. This can be written as negative kq times 1 over r from r to infinity. If we substitute the values of the limits, we obtain negative kq times 1 over infinity minus 1 over r. 1 over infinity gives 0. So, relative to infinity, the potential outside the sphere is calculated as kq over r. Now, we can insert the numerical values into this equation. As a result, we obtain the electric potential at r equals 4.2 centimeters as approximately 9.85 times 10 to 5 volts. B, for r equals 3.2 centimeters, that is for the point on the shell. Again, relative to infinity, we have V at capital R equals the line integral of E dot dr from capital R to infinity. According to the shell theorem, we have E equals K times Q over r squared r hat and dr equals dr times r hat. As in part A, we have kq times integral from r to infinity dr over r squared. The integral of 1 over r squared is negative 1 over r. Thus we have negative k times q times 1 over r. This is equal to negative kq times 1 over infinity minus 1 over capital R. Because 1 over infinity is 0, relative to infinity, we have the electric potential at the surface as kq over capital R. Now we substitute the numerical figures into this formula. The result is approximately 12.9 times 10 to 5 volts. See, at R equals 2.2 centimeters, which is less than the radius of the shell, therefore it is inside the spherical shell. According to the shell theorem, we know that there is no electric field inside the metallic sphere. Therefore, from R equals 0 to R equals capital R, we have electric field as 0. And from part A, we know that for R greater than or equal to capital R, we have E equals kq over R squared R hat. Anyway, relative to infinity, the potential at R is calculated by the formula, the line integral from R to infinity, E dot dr. If we study this integral as inside and outside the sphere, that is, the sum of the integrals from R to capital R, E dot dr, from capital R to infinity, E dot dr. The first part is 0, since E is 0 inside the sphere. And the value of the second part is approximately 12.9 times 10 to 5 volts as found in part B. That is, relative to infinity, the electric potential at the surface. Finally, relative to infinity, the electric potential at R equals 2.2 centimeters is equal to the value at the surface, which is 12.9 times 10 to 5 volts. Okay, that's all about this problem. Thank you for your attention. See you in the next video.